So let's move forward and talk about, okay, we've just done it with a test voltage, color-coded in purple. Let's now do it with a test current, color-coded in green. So we're going to turn off all the independent sources. And now we're going to apply a test current this time, which I'm color-coding in green. And this test current is I naught. We could set it to any value we want. This could be 320 nanoamps or whatever. And if you go through and you find the voltage V naught and you find the ratio of those, you'll get the correct resistance. Since it doesn't really matter, why don't we just set it to 1 amp? And that could make our calculation simple. What we want to find then is if we apply 1 amp of test current into there. Now keep in mind, remember what's going to happen. You're going to apply 1 amp of test current in there. You got an amp flowing through that 2 ohm resistor. Some of it's going to split up this way. Some's going to go that way, some down here, and some of it's going to go through VX, through that 4 ohm resistor, VX, which is going to allow this guy to start to energize. And ultimately, what's going to happen is that there will be some voltage developed across the port. This V naught here will develop across the port. That's actually what we want to find in this particular example. And the ratio of those values. So the equivalent subcircuit over here, again, this time we're going to draw it a little bit different because now we're applying a test current. But when we apply that test current, oops, it's the wrong color. When we apply the test current, I naught, ultimately this is going through some circuit, some equivalent circuit that represents R Thevenin. And what we want to find is the voltage that develops across that whole thing, V naught. And as we wrote last time, the Thevenin resistance, R Thevenin, is going to be equal to the voltage, V naught, divided by the current I naught. Okay, the formula is the same as the last example. The difference here is that we're injecting current into the port and finding the developed voltage across the port, instead of last time we connected a voltage across the port and then found the current, the resulting current. Okay, so let's then go ahead and we can start to solve this thing. So let's do the nodal analysis at, we still have that super node. We've got 2 points here. We've got VX, and I'm going to still call this VA. Okay, we've grounded this here. And this is, we're doing a super node at VX and VA. So on the VX side, we've got 0 minus VX over 4. On the VA side, again, we have 0 minus VA over 6. Plus, now in this case, we've got 1 amp of current flowing through there. So we can actually just say we've injected 1 amp of current flowing through the 2 ohm resistor there. So we can actually just add that in as a current in our nodal analysis equation. So this is a minus VX over 4. Again, VA is, remember that where VA is equal to 3VX. So we've got a VX over 4 minus a VX over 2 plus 1 amp is all equal to 0, which gives us an equation that says 3VX equals 4. And therefore, VX is equal to 4/3 of a volt, and VA is then 4 volts. Okay, I know I went kind of quickly through that, but you've done nodal analysis a lot by now, and that was pretty similar to the equation we did on the last page. Okay, now we want to find V naught, and I'm going to say we're going to find V naught with what I sometimes refer to, you guys have heard me refer to as a mini KVL, meaning that we're going to start at the point VA, and we're going to walk across the 2 ohm resistor to get to the point V out, if you're with me there, right? So it's V out is equal to whatever the voltage across VA at VA is, plus the drop across the 2 ohm. Why is it plus? It's plus because the current 1 amp we injected was flowing towards the left. So as we walk from VA to V out, we're moving against the current, we're gaining in voltage. So VA we already found is 4 volts. We just found that down here. Plus the drop across the 2 ohm resistor. Well, I naught, 1 amp of current is flowing through the 2 ohm resistor. So 1 amp times 2 ohms gives you the voltage. So that's 4 volts plus 2 volts, or in other words, 6 volts. Now we've got our Thevenin. Remember our Thevenin equation is just V naught over I naught, which is 6 volts, as we just found. I naught we applied was 1 amp of test current. So that all equals 6 ohms. And that's the same thing we got on the last example where we applied a test voltage and found the resulting current. The ratio of the test voltage to the resulting current was 6 ohms. On this time, when we applied a test current and found the resulting voltage, the ratio of the resulting voltage to the test current was again 6 ohms.